All right, this is Trig Unit 2, Topic 1 on radian measures still. Actually, we're slowly moving into Topic 2 as well, but I did want to review some stuff from Topic 1. First off, we now officially have our unit circle with all of our important degrees on the inside here and all of our important equivalent radian measures as well. So this is a very, very helpful unit circle. So hopefully you could take this unit circle and answer tons of problems. For example, I could say, what is sine of 7 pi over 4? So that's the angle 7 pi over 4. Your eyes should go directly to 7 pi over 4, and sine is the y value. So the answer to that would be negative radical 2 over 2. I could ask you some maybe slightly advanced questions. What is secant of 5 pi over 6? So again, the 5 pi over 6 is telling you where to look, and we see 5 pi over 6 right here. And we say, okay, secant is the reciprocal of the x, the reciprocal of the x. So that would be negative 2 over radical 3. That's the reciprocal, right? Well, of course, that's an okay answer, but we'd prefer to get rid of that radical, so we would actually end up with negative 2 radical 3 over 3 as our final answer. We could then ask you some advanced questions like what is cosine of 21 fourths pi? Now notice 21 fourths pi is not on here, but because it is in force, it is coterminal with an angle on this unit circle. So my suggestion would be to take a calculator and type in parentheses 21 fourths. Do not put the pi, because then you won't be able to convert it back to a fraction with pi, because it's going to be irrational. And just subtract 2 until you find an angle that is on the circle. So I subtracted 2 twice, and I got 1.25, which is 5 fourths pi. So basically 21 fourths pi is the exact same or coterminal as 5 fourths pi. So now I know where to look, 5 fourths pi, and cosine is of course the x value, negative radical 2 over 2. Alright, I could then also do another one here. I could say, hey, what is tangent of 28 thirds pi? Same thing, I don't see 28 thirds anywhere on my unit circle, so I'm going to go to my calculator, type in 28 thirds in parentheses, and subtract 2 repeatedly until I get something that I do recognize, and the first angle I come to that I saw was 4 thirds pi. So 28 thirds pi is basically the exact same angle, or coterminal angles, with 4 pi over 3. So tangent would be the y divided by the x, so if I take negative radical 3 over 2 divided by negative 1/2, and I do the dirty work, you end up getting positive radical 3. So you're going to have a quiz that's going to cover basically a bunch of problems like that. Hopefully that you understand how to use the unit circle to find them. Okay, next up I want to move on to some new stuff. Kind of this is going to be more topic 2 stuff, and topic 2 is really more about applications of radian measures. So we're still talking a lot about radian measures, talking about some applications. So the first thing I would talk about is when you're dealing with circles, and we draw, oh, that's pretty ugly. Let me redo that here. Not that it's that ugly. I wish this program was able to make circles for us, but it doesn't for whatever reason. But anyway, if here is my radius, and I say this radius is 6 inches, and here is an angle, and this angle theta right here creates an arc length that is, I don't know, let's say 28 inches, okay? And I want to be able to find that angle. I want to be able to interest in that angle. And remember, the idea of radians is that we can find angles based on arc length and radius. So we know that theta in radians, that's important, would be the arc length 28 divided by the radius 6. So 28 divided by 6 is 4.6 repeating. So I'm just going to reduce that, both of them divisible by 2, so I get 14 thirds. So I don't want to give an approximation here because it is a repeating decimal. So we'll say 14 thirds radians. Note that's in radians, okay? If you wanted to convert that, you can just take the 14 thirds and times it by 180 degrees over pi. And obviously there's no pi to cancel, so I'm going to type in my calculator 14 thirds in parentheses times 180 over pi in parentheses, and I get that it is approximately 267.38 degrees. That is how big that angle is. And that does look like it would make sense. That angle does look approximately 267 degrees. So that's all fine and dandy. Well, the next thing we want to be able to do is find what we call sector area. So let me first explain what a sector is. Anytime that you create an angle in a circle and you create this arc length, the chunk is, or like the slice of the pie, you could think of it as a pizza pie, would be what we call the sector. So this is the sector. The sector is the entire chunk there, okay, of the circle. And a sector has an area. Now we're not, arc length. Arc length is just the distance around the edge. So area is actually the entire values inside. So when you're dealing with, if I want to find the area of that sector, the formula for area is area equals 1/2 r squared times theta. Okay, but we have to understand that it's really important to understand that this theta must be measured in radians because it all comes down to arc length and radius. Okay, so it's really important to understand that that theta is measured in radians. If you would forget to do that, then you're going to have an incorrect answer. So if I would give it to you in or in degrees, you'd have to convert it. So if I wanted to find the area of this sector, it would be 1/2 times 6 squared. That's the radius squared times the theta measured in radians. We already figured that out. Theta was 28/6 or 14/3 radians. So there it is right there. So if I want to use my calculator, I'm going to type in 0.5 times 6 squared times in parentheses 14/3, and I get that the area is amazingly nice, perfect 84. Would be the area there. So hopefully sector area makes a lot of sense. It's for the most part pretty easy. I would like to look at another example here just so that everybody, I guess, completely understands how sector area works here. So let me find a good problem here for you. Okay, let's slide down here so I can have a new blank slate here. Let's say that we have a sprinkler. Okay, and old sprinklers, not necessarily old sprinklers, but sprinklers like out on golf courses, you have the sprinkler head right here, and that sprinkler head sprays out water, and as it's spraying out that water, it's traveling in an arc, okay, and that sprinkler head is set to some degree to rotate back and forth. So all of this stuff here is getting wet. This is all the grass getting wet as that sprinkler head moves. So let's say the sprinkler head is shooting out water at 50 feet. Okay, and let's say that that sprinkler head is rotating. Okay, so it's rotating back and forth at a 75-degree angle. So it's rotating at a 75-degree angle. And it's hard to see in there, so I'll just write down that here. That's rotating at a 75-degree angle. And I want to know what area of the grass is actually getting wet. So the area formula is 1/2 times the radius, and the 50 foot is the radius that is spraying out and forth. So that'd be the 50 squared times theta. But I got to be careful here because theta needs to be measured in radians, and it's currently measured in degrees. So 75 degrees is nice. It makes sense to us. We could visualize 75 degrees, but in order for the formula to work, it needs to be in radians. So I'm going to convert this to radians real quick by multiplying by pi over 180 degrees. So that gives me 75 pi over 180. The degrees cancel, so all I got to do is reduce the 75 over 180, and that reduces to 5/12 pi. So 75 degrees is the same thing as 5 pi over 12, or 5/12 pi. So that is what I need to utilize here in the formula. Okay, so when I go to my calculator, I'm going to type in 0.5 times 50 squared times, in parentheses, 5 pi over 12. And I get that it's going to cover an area of 1,636.25 square feet, or feet squared. Okay, so that's a big chunk of area there, and this is spraying out pretty big. So that is how much grass is getting wet. So notice again, I used the formula 1/2 r squared times theta, but theta must be measured in radians, and of course it was given to me at 75 degrees, so I had to do a quick conversion there. So hopefully sector area makes sense. That's a formula that you guys are going to have to memorize. Area is 1/2 r squared times theta, and that should be it. Make sure you understand theta is in radians. All right, moving on. The last concept here is going to take a little bit of time to talk about, but we're going to talk about linear speed and angular speed. And when we're talking about linear and angular speed, we're talking about the speed of an object as it travels in a circular path. Okay, so think about objects that travel in a circular path, like Ferris wheels travel in a circular path. I guess I could say protons kind of travel in a circular path, and I'm not a chemistry teacher, know how much that's true, but as they travel around an atom. We also have merry-go-rounds travel in a circular path. Technically, race cars, that's more of an oval path. I guess if it was a pure circle track, which there aren't really any of those. But anyway, you get the basic idea of things that travel in a circular speed. Oh, another thing is hands of a clock. Hands of a clock travel in a circular path. So anyway, when we're talking about linear speed is something that we're very familiar with. Linear speed is distance over time. So an example of linear speed that you guys probably see every day would be, in a car, miles per hour. So that's distance miles divided by time hours. But it's not limited to miles and hours. It could be feet per second, millimeters per second, inches per minute, as long as it's a distance divided by time. Okay. Now, when we're traveling in a circular path, we're usually thinking about the total distance to go around a circular path would be the circle's circumference, and how much time would it take to go around that entire circle. Okay. Angular speed is the radians per unit of time. So angular speed is how many radians per unit of time is that object traveling. So as that object's traveling, so think about an object that's traveling in this circular path, right? It's traveling in this circular path here. As that object is moving, its speed is its linear speed, right? That's distance per time. And it also has an angular speed because this angle, right? Here's the object right here. Maybe I'll use a different color so you can see it. Here's the object right here, and as it's changing, the angle theta here that's changing. So as it moves around this path, that angle is getting bigger, 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 and then it keeps going around and around. That angle is constantly changing, and the faster an object's going, the faster that angle is changing, and the slower it's going, the slower that angle is changing. But the angular change of an object is its angular speed in radians per time. So hopefully that isn't too confusing, but let's look at an example here. Let's talk about a merry-go-round. And let's say that we have this merry-go-round here, and here's little Susie, and Susie is on that edge of the merry-go-round, and that merry-go-round has a radius of 12 feet. So it's a pretty big merry-go-round, okay? So she's traveling around this thing. Now, she's not technically going anywhere because she's trapped in this circle, but she is moving, and if she's moving, then she has a linear speed, okay? So we have to be given something here. Let's say that the operator sets this machine to go 1 revolution every 8 seconds. So every 8 seconds, this Susie's going 1 full rotation around this circle every 8 seconds. So if I ask you what Susie's linear speed was, we got to think about how much distance does she cover in those 8 seconds. Well, that means every 8 seconds she goes all the way around the circumference of the circle. So the circumference for Susie would be 2 pi times 12, or 24 pi, and that would be feet. So the circumference of Susie's path is 24 feet, and she's doing that every 8 seconds. So her linear speed would be 24 pi feet every 8 seconds. And of course, that would reduce to 3 pi feet per second. Now, it's not always going to reduce so nice, but she's traveling 3 pi feet per second. Now, if we actually approximate what that would be, 3 pi is approximately 9, so I'll put the little approximate here, 9.42 feet per second. 9.42 feet per second. So that is how fast Susie is going. So she's going about 9.5 feet every second in terms of traveling. One question, to me, that makes sense, but I want to know how fast is Susie going? So what would be her miles per hour? So let's start back with this 24 pi feet every 8 seconds that Susie is traveling, okay? Now I want to convert this to miles per hour. So I need to first convert seconds to hours. And I'm going to do that by putting seconds on top. I know there are 60 seconds in every 1 hour, and that is just a conversion factor you guys should know. Whoop. I take that back. That's 60 seconds in every 1 minute. So then the seconds cancel, and now I need to convert those minutes to hours. So I know there's 60 minutes in every 1 hour. Sorry, I almost messed that up. So anyway, that's my conversion factor there. So I took the 24 pi feet per second I knew she was traveling, and I'm converting the seconds to minutes and the minutes to hours. So I'm now in hours. Now I got to get those feet to miles. And I know the conversion is I need feet on the bottom so that it cancels. I want the feet to cancel. I know there's 5,280 feet in every 1 mile. So now if I do this calculations, and the easiest way to do this calculation is to go straight across the top. So it'd be 24 pi times 60 times 60. And then you could times it by 1 if you need to, but obviously I can change it. And we're going to divide it by, in parentheses, 8 times 1 times 1 times 5,280. Obviously, you don't need to multiply by the ones, but you get the idea. So I've taken all the top in parentheses, divide all the bottom in parentheses, and I get that she is going 6.43 miles per hour. So now that makes sense to me. She's going 6.43 miles per hour. I can actually get a feel for that. That's, moving in a car 6 miles an hour is pretty slow. Well, it's a merry-go-round. Merry-go-round's supposed to be nice and slow rotation, okay? Now let's go back to this problem here and let's try to figure out her angular speed. Angular speed is simply how many radians she is traveling per unit of time. So her angular speed, it's actually really easy. It shouldn't be anything difficult. How many radians did she go? When she goes that one full rotation, that is 2 pi radians. So that means that she travels, in terms of angles, she travels 2 pi radians every 8 seconds. So there's her unit of time there. So she is going, you could reduce that to pi over 4 radians per second, and if you really wanted to approximate that, you can do pi divided by 4. So she's going approximately 0.79 radians every second. So her angle is changing. Now, to be honest, notice the one thing that didn't matter here was the radius. The radius actually has nothing to do with angular speed. If Susie was sitting in here on the inside, let's say Susie was sitting inside, obviously her linear speed would be changing. Okay, but because the radius affects your linear speed. But if Susie was sitting inside here, her angular speed would not change, because no matter how big the circle is, when one rotation around any circle is always 2 pi radians. That's not going to change. But obviously, if Susie was sitting closer, she's going to be moving faster. So if you're on a merry-go-round, you'll notice if you're on the edge, you're moving slower because you got a bigger distance to cover. But if you're inside, you're going to be moving pretty fast. So it's kind of like those merry-go-rounds on playgrounds. If you're sitting in the middle, you're spinning really, really quick. But if you're on the edge, you're kind of spinning a little bit slower. So linear speed changes based on radius, but angular speed does not. So hopefully that example makes a lot of sense, I guess. Let's take a look at another one just real quick here. Another one that I like to think about is a car. So let's say that we have a car. Okay, here's my beautiful car. And there's my car. Okay, and we think about these tires, okay? The radius of this tire right here, or actually most cars, the tires are talked about in diameter. We just have to cut it in half to find the radius. But let's say the diameter of this car wheel is 1.5 feet. So the diameter is 1.5 feet, okay? And we know that the car is traveling 65 miles per hour. Okay, so one question I can ask you is, how many revolutions is that tire going? So how many times is that tire spinning? Okay, this is its linear speed right here, 65 miles per hour. I want to know how many revolutions it's spinning. So I got to think, okay, it's going 65 miles per 1 hour. So there's my linear speed right there. And I need to figure out how many revolutions it's traveling, right? So let's see here. I need to change miles to revolutions, right? Well, the issue is I got to think about revolutions. I know that 1 revolution of this tire is equal to the circumference of the tire, which is 2 pi times the radius. Now, the radius is 1.5 divided by 2, or 0.75. Okay? So it's 2 pi times the radius, and then actually if you figure that out, the circumference is 2 pi times r, or another way of looking at circumference is just the diameter times pi, because 2 times r is the diameter. So anyway, 2 times the 0.75 would make 1.5 pi anyway. So the revolution is in 1.5 pi feet, because that is the circumference measured in feet. Well, I'm currently in miles, so real quick I got to change those miles. I know that 1 mile is 5,280 feet. So if I convert those miles to feet real quick, now I could say that I know that 1 revolution is equal to 1.5 pi feet, and that's the circumference, right? So I know that 1 revolution is equal to 1.5 times pi feet. Now the reason why I put feet on the bottom is because I wanted it to cancel, so I need to be across from it to cancel. So this is going to actually leave me with how many revolutions per hour. So if I do 65 times 5280, that's the top, divided by the bottom I got to put in parentheses, 1.5 pi. Basically this tire is going about approximately 72,829.30 revolutions every 1 hour. So every 1 hour I'm driving, that tire has actually spun around almost 73,000 times. Okay, now that we might want to reduce this a little bit more. Like, for example, how many times it revolves per hour is a little bit weird. Let's figure out how many times it revolves per minute. That might make more sense to us. So I'm already in revolutions. Now I just got to get the hours to minutes. So if I can just continue with my conversion here, I know that 1 hour, I put it on top because I want it to cancel, is equal to 60 minutes. Okay, so now this would be in revolutions per minute. So basically I'm going to take the 65 times 5,280 again, but this time I'm going to divide it by, in parentheses, 1.5 pi times 60, and basically dividing by 60 is going to convert this to how many revolutions per minute. Okay, so that's going to be 1,213.83 revolutions per minute. So next time you're driving down the highway 65 miles an hour, think about how fast those tires are spinning. I mean, they're spinning 65 miles an hour, but think about how many times they're spinning, and every minute those tires are spinning 1,213 times. So that's kind of some applications here, and the idea is understanding that 1 revolution is equal to the circumference. If I want to know the angular speed, I got to start with the 65 miles per hour. Okay, and let's say I want to know how many, as long as time is on the bottom, you're technically in a speed. I just need to get radians on top. So the first thing I got to think about is I got to convert this to feet, because again my circumference is measured in feet. So I got to think that this is 1 mile is 5,280 feet. Okay, so let's see here. That's going to convert me to feet, and I know that 1.5 pi feet is equal to 1 revolution. But I want that to be in radians, right? So I'm going to erase that, because I know that 1 revolution is 2 pi radians. So every time this circle goes around 1 revolution, which is 1.5 pi feet, it's also going around 2 pi radians. So multiplying here should make sense. So again, I get 65 times 5,280 times 2 pi. And then in parentheses, I'm going to divide it by, in parentheses, 1.5 pi. And I get, oh boy, I get a big answer here. I get 457,600. And that would be radians per hour. Okay, and you might want to convert those hours to minutes by dividing by 60, but you get the idea that this tire is moving really, really fast. That angle is changing extremely, extremely fast. So hopefully a couple of those problems made sense. Hopefully you understand sector area. Hopefully you understand angular speed and linear speed. It's all about the circumference of the circle and how fast it's traveling. So anyway, we'll do some examples in class like that, and we will have a quick quiz again over that first stuff, over just sine, cosine, tangent stuff from the unit circle. So all right, hope you enjoyed the video. Hopefully it made sense, and I'll talk to you guys later. Bye.